Okay, good morning, guys. So I'll be solving, we'll be enriching again our topic about nuclear chemistry. So we have this problem. Excuse. You have cesium-137 has a half-life of 30.2 years. How many years will it take for a 100-gram sample to decay to 0.01 gram? So we'll go back to our equation in deriving that for nuclear chemistry. I think I've opened it already. So I think the last time I didn't give you the whole of it. Anyway, it's in the book. So this is how it has been derived for half-life. That is computing for the constant for every compound because it's discussing. But as you can see for the discussion on the book, there's that derivation actually is only for half-life. Now, if we want to use it just like this, how many years? So basically, it's not half-life. The problem is how many years, okay, for a 102.01 gram of your material to decay. So we will go back to the original equation, not necessarily to the differential equation. We can do that, but I think it would be harder for you. So let's just use the algebraic form. As you can see, this derivation will give you actually, this one is for your half-life already, meaning your N or uh, original concentration of your substance. And this is your after half will be depleted. So it says the original half of that. So this meaning this is the new concentration at that half year. So if this is not half, so we can actually use that one. We can say because your NO is mole per liter. This one also this is actually your product. Again, your K is actually your product. This is your I mean the original over your new at a particular yield. Maybe we can go back to the algebraic form actually. Okay, we can go back to the original form. We can say that your loan, this is the concentration of your um the concentration now. So that is the concentration, new concentration, original, sorry, the original concentration CO all over the new concentration. Concentration after a period, yet let's say a year. So now we will be talking about maybe not year, time. Okay? Maybe a particular time, CT. And then actually this now talks about the 100 grams because we're not talking about half-life anymore, but we will still be using that because the derivation for your K is using half-lives, okay? Because they derive constant for it. CT now would be the point zero 0.01, okay? That's what it means from that equation. You can, of course, look at the derivation, how they derive the half-life. But since now it would be equal now to K, of course, that K is still constant for that particular nuclide. And then now, your T now is your not half-life. So, T might be, according to this T, that T years when the concentration would be 0.01. Actually, here is the mass. But again, since if the volume will not change, basically this is mole per liter, and this is also mole per liter. This volume will not change, so we can just rule it out because volume not change, meaning you're just having a ratio of your mole of your reactant original over the mole what is remain. Okay, but since again, if this is the same compound, that mole, we know that mole is mass over atomic weight. If this is the same compound, so basically we can still rule out the atomic weight, mass all over the atomic weight, because of the same compound. So now we'll be dealing the mass original and the mass new, mass at time t. Okay, so we can just plug it actually at alone the mass, or actually will just be the mass original Because actually I have to do this because the complexity really lies in here. What if you're not talking about mass, you're talking about mole? What if you're talking about concentration? So you definitely have to discuss this one. Diri pwede kita magdiretso nga mass ito iya. No. You have to go back to kinetics or probably from your equilibrium constant. Nag-discuss na kita ito in equilibrium. It's talking about moles. But here, for special case, this is special one, it would be mass. Original all over the mass at time t. Okay? And then it will not be equal to kT. How about kT? You go back to the definition of your half-life. That kT, your T1 half, because this is a constant now, that is equal to ln 2 all over K. Ato ito ato equation. Man, niya. Ln 2 all over K. Or you can say that your K, because your T1 half is constant and also your K is constant, you can compute vice versa. Okay? So, kung half-life ang ginataga aton, so you will be say ln 2 all over half-life of 1 half, which is, ln 2 again is a constant. Maupay takagi. Gamitan ko dali. Okay? Ln 2, you have your 1 half. Inutro ko lang. Ln 2 all over 30.2 years. Okay? Maupay takagi. 30.2 years. Is it correct? So that is 30.2 years. So you now already have your K. We can substitute it to this uh, problem or from that equation. So ln now, that is your 100 grams all over 0.01 gram. 0.01 gram is equal now to ln 2 all over 30.2 years. And then multiplied by t. Now we're solving for t. So therefore, we can say that t is equal to 30 30.2 years all over ln 2 multiplied by, again, this is algebra, ln 100 grams all over 0.01 grams. So that. So using your calculator, okay? So the answer is 401 years actually into significant figures. I do believe that it's because of the 100. So you have two significant figures, so that would be a 400 years. Okay? So that's the answer of that problem. Thank you guys. Thank you guys for listening. Sorry.